Section 8.5 is called power series. So a power series is a series as a function. What I mean is if you look at the form it has, it's a summation going from 0 up to infinity of some type of coefficient times x, which is our variable, raised to the nth power. So it's a function of x. If we were to expand this, when I plug in that n is 0, I would have some constant c0, x to the 0 power, which is just 1. That's why this first piece is just a constant. When I plug in that n is equal to 1, I would have the coefficient c1, x to the first power, and so forth. Let's look at an example of this. So let's consider the series going from 1 up to infinity of x to the n minus 1 power. And I want to take a second and just look at what this would be if I were to expand the series the way that it is now. So notice this summation starts at 1. When n is equal to 1, I would have x to the 1 minus 1, or the 0 power, meaning my first term is just 1. When I plug in that n is equal to 2, I would have x to the 2 minus 1 power, so I'm just getting x. It is a summation, so I'm adding the terms. For the third term, plugging in that n is 3, I would have x to the 3 minus 1, meaning I'm getting x squared. So this series looks like 1 plus x squared, and so forth. If you're looking at the form of our power series, notice this summation starts at 0. So if I'm considering this example, and I want to know, is it related to a summation that starts at 0? In other words, can I rewrite this sum to start at 0? Well, I definitely want to have x raised to some power, and the first term that my series generates needs to be a 1, or an x to the 0 power. So if I'm starting at 0, and I raise x to the 0 power, I am in fact getting 1. Now when I go to the next term, n equals 1, and I plug in, I have x to the first power, x to the second power when n equals 2, and so forth. The idea is if I drop the summation to start 1 beneath, I account for that by adding 1 to the power on x inside. One nice thing we want to note is that power series are in fact a variable raised to a power of n. So it makes sense after our last section when I work with these and I want to talk about their convergence that variables to powers of n should make you want to think about the ratio test. So we're going to keep that in mind as we move forward in this section. If we want to talk about the convergence of power series, there are 3 possibilities. So a power series can converge at one number when x is equal to a, meaning when you have 0 raised to the power of n, you are adding a bunch of zeros. Of course, you have some type of convergence there. So it can converge for one number. It can converge for all real x, so it could converge for all numbers. Or it's possible that the series converges for some numbers. Right? The main thing to take away from this box is that every power series has some form of convergence. Either it converges at a point, it converges for all real numbers, or it converges for some range of numbers. Now, if the series converges, then if I have the absolute value of x minus a less than some number, that number is called your radius of convergence. Examples: if your series converges for one particular value, then it does not converge for anything outside of those values. Your radius of convergence is actually 0. It only converges for one value, and you would just list what is that value. If your series converges for all x, then your radius is infinity. So it will converge for any value, whether it's positive infinity all the way down to negative infinity. If it converges for some values, then your radius of convergence is just going to be a number. We can also talk about an interval of convergence. So if I'm on a number line, let's look at an example. And maybe the center that I'm talking about is the value 1. And let's say we found that our radius of convergence was 3. What this means is that anything 3 units within 3 units of 1 is going to make the series converge. So 3 units to the right of 1 would put us at 4. 3 units to the left of 1 would put us at negative 2. So anything on the interval negative 2 to 4 is going to have my series converging. We do have to talk about what happens at the endpoints negative 2 and 4. Here's our first example. We want to find the values for x for which the following series will converge. Find both the interval of convergence and the radius of convergence. The series they give me is a series going from 1 up to infinity of x minus 3 to the n divided by n. They want to know, where does this converge? So again, I'll mention I do have a variable being raised to powers of n, so I'm already thinking about using our ratio test to talk about where does this converge. The ratio test says I look at the limit as n goes to infinity of the absolute value of the an plus 1, meaning the sequence inside with n plus 1 plugged in, divided by the sequence itself. So for us, I have the limit as n goes to infinity. Absolute value, this inside sequence with n plus 1 plugged in, would be x minus 3 to the n plus 1 divided by n plus 1. I'm wanting to divide this by the sequence itself, x minus 3 to the n over n. Of course, a fraction inside of a fraction, I'm going to flip that bottom fraction, and in the future I'll just automatically write that step. So I have the limit as n goes to infinity, absolute value, x minus 3 to the n plus 1 divided by n plus 1 times n over x minus 3 to the n, close absolute values. You should notice several things are canceling. Here I have x minus 3 to the n plus 1. It's raised to the n in the denominator, so they are all canceling except for one of the x minus 3's. I have the absolute value of x minus 3. I'm going to pull this limit in next to the n's. So here I'm left with that n over n plus 1. Of course, I can drop the absolute values because I know n was positive, right? It started at 1. Well, limit of this is going to go to 1. So what I'm left with is the absolute value of x minus 3. Now, I want to know, when is this series going to converge? With the ratio test, I know that happens when this is less than 1. So I'm forcing this to be true because I'm trying to find out what values of x make this series converge. Well, absolute value of something less than a number would tell me that it's the negative of the right-hand side, less than the inside of the absolute values, less than the right-hand side. Solving this, I'm going to add 3 to all of the pieces. So I'll have negative 1 plus 3 is 2, is less than x, is less than 1 plus 3, which is 4. So I know that this series is going to converge for values between 2 and 4. We have to talk about what happens at the values, or the endpoints, 2 and 4. The answer is we have to check those. Well, what I mean is I actually want to let x equal 2 and see what happens to our series. I want to let x equal 4 and see what happens to our series. So looking at our given series, it is the series going from 1 up to infinity of x, which I'm plugging in as 2 minus 3 to the n over n. Simplifying, I'm looking at the series of negative 1 to the nth power divided by n. I want to know, what does this series converge? You should notice that it's an alternating series. Couple different ways you could think about it. I'm going to go with the alternating series test, which says I want to consider the non-alternating part of the sequence inside, that 1 over n, and I want to know, is this a decreasing sequence? We've worked with this one before several times. You know that it is. Alright, so let's look at a few of the terms. If I wanted to look at B1, it would be 1 over 1. B2 would be 1 over 2. B3 would be 1 over 3. It is definitely decreasing. I also want to look at the limit of that sequence. So I'm talking about the limit as n goes to infinity of 1 over n. We know that that equals 0. Alternating series says that this does converge. Right? So when I plug in x equals 2, it converged. This means I want to include x equals 2 in my answer. When x is equal to 4, I'm taking my given series, which was the series going from 1 up to infinity. X is 4 minus 3 to the n over n. Simplifying, I have a sum going from 1 to infinity. 1 to the nth power is just 1 divided by n. This is our harmonic series, which you should know diverges. What that means is I don't want to include x equals 4 in my answer. So values of x that work, anything between 2 and 4, including 2 but excluding 4, your interval of convergence. Including 2 all the way up to 4, not included. The radius of convergence, we could have seen this all the way up here. But I like to give a little sketch to relate the two. So here I have the interval from 2 to 4, and we can indicate I'm including 2 and excluding 4. I want to know, what is the radius that corresponds to this interval? Well, if I wanted to find the middle of the interval, I would have 4 minus 2 divided by 1. It says that each of these distances is 1, meaning this is centered at 3 and it has a radius of 1. We have found the values of x for which this series converges. Part B. Here I have the series going from 1 up to infinity of x to the n divided by n times 3 to the n. Again, the question was, what is the radius of convergence? What is the interval of convergence for this series? I see the variable being raised to powers of n, so I'm already thinking about using the ratio test to answer this question. Again, the ratio test says I'm going to look at the limit as n goes to infinity, absolute value of the sequence with n plus 1 plugged in, divided by just the sequence. This is going to be equal to the limit as n goes to infinity. An plus 1 is just what I see here, but replacing n with n plus 1. So I have x to the n plus 1 divided by n plus 1 times 3 to the n plus 1. Now, this is being divided by what you see inside. Fraction inside of a fraction. I'm going to go ahead and flip this bottom fraction. So it becomes multiplication. An used to be x to the n over n 3 to the n. Flipping it, it is n 3 to the n over x to the n. Just saves us a little bit of writing. You should notice things are canceling out. I have n x's in the bottom and n plus 1 in the top, so I have one up top still. have 3 to the n up top, 3 to the n plus 1 in the denominator, meaning I have an extra 3 in the denominator. I still have this n in the numerator and this n plus 1 in the denominator. So what I'm looking at, pulling out this absolute value of x over 3, I have the limit as n goes to infinity of n over n plus 1. We know that limit is just 1. So I'm looking at the absolute value of x over 3. And you can drop them on the 3 if you want. I want to know, where does this series converge with the ratio test? I know that happens when this is less than 1. So again, I'm forcing this to be true to find those values of x that make this converge. Absolute value of something less than a number means that number's negative sign is less than what you had inside the absolute values is less than the number. I'm solving this for x, so I'm going to multiply every single piece by 3. So negative 3 is less than x is less than 3. I need to know what happens at these endpoints. So I want to check what happens when x is equal to negative 3, and I want to check what happens when x is equal to 3, so I can know if I include them or exclude them. Well, when x is equal to negative 3, I'm taking this original summation and just plugging negative 3 in for x. So what I'm looking at, my sum is going from 1 up to infinity of negative 3 to the n, being divided by n, 3 to the n. Just to make it easy to see what's happening, notice this is the same thing as negative 1 to the n times 3 to the n, divided by n, 3 to the n. You should see that the 3 to the n's are canceling. So I'm looking at the series going from 1 to infinity of negative 1 to the n over n, and I need to know, does it converge or diverge? This is the exact same one we worked with in part A. You'll remember we used the alternating series test. We said the sequence 1 over n was decreasing. And we said that the limit of that sequence, 1 over n, does in fact equal 0. So this series converged. Meaning I want to include x equals negative 3. Let me just rewrite that a little clearer. I want to include x equals negative 3 in my answer. When x is equal to 3, I'm going to take again that original series and plug in 3 for x. I would have a series, it's going from 1 up to infinity of 3 to the n over n 3 to the n. Immediately we should see that the 3 to the n's are canceling. So I have a sum from 1 to infinity of 1 over n. Again, this is our harmonic series, which we know diverges. So I don't include x equals 3 in my solution. So for my interval of convergence, I'm going to denote that I of c, interval of convergence. It's going to go from negative 3, which I want to include, up to 3, which I don't want to include. If I want to talk about the radius of convergence, again we could sketch this. I have negative 3 up to 3. The center of this is 0, and our radius is 3. So the radius of convergence, 3 units to the right of 0, 3 to the left, it will all converge. Part C. I have another series. It's going from 1 to infinity of 4x to the n divided by n factorial. Again, I'm going to use the ratio test to talk about where does this series converge. That means I want to look at the limit as n goes to infinity, absolute value of an plus 1 divided by an. an plus 1 is this sequence inside. Everywhere you see an n, I now want to put in n plus 1. So I have 4 times x to the n plus 1 divided by n plus 1 factorial. Now this is being divided by an, so of course I'm going to take that bottom fraction, flip and multiply. So this is going to be multiplied by n factorial over 4x to the n. You should notice the 4's are canceling. I have n x's in the bottom, n plus 1 in the top, so I still have 1 in the numerator. And let's talk about the n factorial and the n plus 1 factorial. So n plus 1 factorial, if I wanted to expand it, is n plus 1 times the next integer down times every integer beneath it to 1, also known as n factorial. You should notice the n factorial in the numerator and the denominator cancel, and you're left with that n plus 1 in the denominator. So what I have is the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. Notice as this numerator goes to infinity, this fraction is going to 0. Anything times 0 is going to be 0. Now, when is 0 less than 1? Well, that is always less than 1. So what this means is that this works for any x. This series converges for any x, meaning your interval of convergence, it can be any value or any real number, so negative infinity to infinity. Your radius of convergence would be infinity. Part D. I have the series from 1 to infinity of n factorial times 3x minus 4 to the n. Again, I'm seeing variables to powers of n and factorials, so I'm already thinking about a ratio test to decide where does this converge. Ratio test says I want to look at the limit as n goes to infinity, absolute value of an plus 1 over an. An plus 1 is just the sequence inside. Everywhere you see an n, I want to plug in n plus 1. So I would have n plus 1 factorial times 3x minus 4 to the n plus 1. This is being divided by an, which is just this sequence. N factorial, 3x minus 4 to the n. You should notice that 3x minus 4, there are n of them in the bottom and n plus 1 in the top, so we have an extra 3x minus 4, let me just leave it this way, in my numerator. We'll keep the limit with us for now. In here I have an n plus 1 factorial divided by n factorial. Again, n plus 1 factorial is the same as n plus 1 times n factorial, meaning you should be left with an n plus 1 in that numerator as well. So what I'm looking at is the absolute value of 3x minus 4 times the limit as n goes to infinity of n plus 1. You should notice that this piece is going to infinity, meaning this whole thing just diverged, right? Well, if you're thinking about to the opening of this section, we said that every power series converges in some way. So this series almost diverges. It means that it is convergent at a single point. So power series don't diverge, but they can converge at one point. So again, I alluded to this earlier. What is the one number that I can add up and it will not change values? That's 0. So the question is, what x makes this piece out here, the 3x minus 4, equal 0? Solving this equation for x, I would add 4 to both sides, and then I would divide by 3. So this series diverges, except when x equals 4/3. The way that we write our answer, the interval of convergence, it is actually not an interval, it is a single point, 4/3. And radius of convergence, what values outside of 4/3 will cause this series to converge? None of them. Remember, every power series converges in some way.